So let's see if we can get ourselves off to a good start with inference. I want to go ahead and set out some goals for our session. First and foremost, I want to try to help you distinguish between proper interpretations of confidence intervals and confidence levels. This is something that students get into trouble with right from the beginning. Try to help clarify the underlying logic of significance tests. I want to illustrate the link between type 1 error, type 2 error, and the power of a test using an applet. I'd like to try to confirm what students need to do in order to get full credit on an AP statistics exam pre-response question relating to inference, whether it's a confidence interval or a test. And maybe talk about some specific strategies for helping students do inference correctly. This material comprises about 40% of the topic outline for AP statistics and is weighted accordingly on the exam. So very important that we do what we can to help students be successful. So let's start with the basics. What is inference? Well, one way to look at it is it's about drawing conclusions that go beyond the data that we have at hand. We often say that we use statistics from our sample to draw conclusions about some parameters that we're interested in. There are two main types of inference that we work with in AP statistics. The first type is estimating a parameter, which involves confidence intervals. And the second type is testing a claim of some sort, which is where significance tests come in. And the last thing I wanted to set up, when we're thinking about inference, whether we're doing a confidence interval or a significance test, the scope of inference is determined by the way in which the data are produced. When we use random sampling to produce data, that allows us to generalize our results from a sample to a population. When we do a randomized experiment and we randomly assign experimental units to treatments, that's because we want to draw cause and effect conclusions. It's fairly unusual in a randomized experiment to randomly sample the experimental units that we're going to impose the treatments on. This big idea of scope of inference I like to put right up front, and hopefully you've had a chance to talk with students already about scope of inference based on random sampling and randomized experiments. So this will be a nice review for them about how important the method of data production is in determining what kinds of conclusions we can draw. So with that in mind, I'd like to talk about confidence intervals and confidence levels. What is a confidence interval? Well, one way of looking at it is it's an interval of plausible values for a parameter. How do we construct a confidence interval? Well, being a math guy, I like to get right to the formula. So what we'd like to do is calculate some sort of point estimate based on the sample data, and then add and subtract some margin of error that takes into account the fact that our point estimate's probably not right. It's probably not equal to the true parameter value. And if we repeated the data production process, either the random sampling or the random assignment, we'd get a different point estimate. So there's going to be some variation from one random sample or one random assignment to another when it comes to our point estimate, and the margin of error takes that into account. If you're into my formula game, then another way to think about this is the point estimate is our statistic from our sample, and then we add or subtract some critical value that comes from a Z standard normal distribution or a T distribution times the standard deviation of our statistic. This is the formula that students are given on the AP exam formula sheet. So they need to be familiar with this kind of generic formula. And then they're also given information about the standard deviation of the statistic. So I'm giving you this little chart because we're going to be talking about inference for proportions and also inference for mean. And you can see the different notation: P for population proportion, P hat for the sample proportion. Here's the standard deviation of the sampling distribution for P hat. And in this column, I've included the standard error of that statistic, which comes from replacing the value of P with our estimate that we get from our sample, which is our p-hat. Likewise, in the row for means, we've got the population mean mu, the sample mean x bar, the standard deviation of the sampling distribution of x bar, and the standard error of the statistic Sx divided by square root of n. So we all know that we're going to be using the standard errors when we're calculating confidence intervals, and we're going to be using the standard deviation of the statistic when we do significance tests. So that's a handy little slide. So let's go ahead and get to it. The first thing I want to do is talk about interpreting confidence intervals. I would really encourage you, if you haven't done this before, when you first introduce confidence intervals, don't get too focused on the confidence level too quickly. Talk about what a confidence interval is. So here's an example. 2 weeks before a presidential election, a polling organization asked a random sample of registered voters the following question. If the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favor candidate A is 0.48 to 0.54. So the first question is to interpret the confidence interval. This is where we say we are 95% confident that the interval from 0.48 to 0.54 captures the true proportion of all registered voters who favor candidate A in the election. So we've just interpreted the set of plausible values for the parameter that we're interested in estimating. That is, the true proportion of all registered voters who favor candidate A. Let's continue with part B. What is the point estimate that was used to create the interval? And what's the margin of error? Remember, the formula I showed earlier was point estimate plus or minus margin of error. So we hope students can look at the interval there and say, well, the point estimate must have been 0.51. It's right in the middle of that interval. And then the margin of error would go out from the 0.51 to either end, and that must be about 0.03. That'll put us to the two ends of the interval. So the point estimate is p-hat equals 0.51. The margin of error is 0.03, which is a very common margin of error that you see in large national polls with just over 1,000 people. Part C of our question is looking ahead to other parts of inference. Based on this poll, a political reporter claims that the majority of registered voters favor candidate A. Use the confidence interval to evaluate this claim. So now we're using the confidence interval to make some decision about this supposed parameter value. Well, 0.48 to 0.54, any of those values for the population proportion are believable based on the data. So the reporter claims that a majority of voters favor candidate A. A majority would be more than 0.5. And the confidence interval does include values above 0.5, but it also includes values below 0.5. So there isn't convincing evidence to say that the true proportion P is greater than 0.5. We don't have convincing evidence to support the reporter's claim. So you can preview the logic of hypothesis testing just a little bit by introducing students to it here, making decisions based on a confidence interval and the set of plausible values for the parameter. So I'd encourage you, if you haven't done that sort of example before, to use one, maybe this one, or one like this, to get students used to the idea of interpreting the confidence interval and what it means and how it gets built before you launch into the confidence level. So that's all I wanted to say about the confidence interval. Now I'd like to take a look at the issue of the confidence level, the 95% confidence that I mentioned in the previous example. What does 95% confident mean anyway? So I have a little applet that I'd like to show you. Preloaded all the applets, so you're not going to see me click on the link in the slide and go there. I think it'll be faster if I just go straight to the applet is loaded. This particular one is at the Practice of Statistics 4th edition website. All the applets here are freely available, and so you're welcome to use them. This particular one is the confidence interval applet. And what the applet allows you to do, first and foremost, is set your confidence level. I'm going to leave it at 95% to match the example that I did a moment ago. You click on the sample button here, it will take a random sample, and it will calculate a confidence interval for the population mean. You'll notice this first interval, the value of x bar that we got was very close to the true population mean mu, represented by this vertical line. I'll click sample again, and we'll get a different confidence interval. You'll notice this time the value of x bar is a little bit further away, but the interval still manages to capture the mu. And we can do that a few more times, and you'll notice that so far at least all of the intervals have managed to capture the true population mean. So let me reset, and let me do a bunch at one time. I sampled 50 intervals, and so far 49 out of 50 have actually caught the true mean. Here's another 50, and another. You can do quite a few very quickly live in class for students. And those of you who know the punchline know we're asking them to think about the long-term capture rate if we use this method of confidence intervals. And I should quit while I'm ahead because I had 95 there for a second. So I've done 750 confidence intervals, and 713 of them, which is roughly 95%, have included or captured the true mu. So this idea of the confidence level is the long-run capture rate if we take many, many random samples, and for each of those random samples calculate a confidence interval. 95% of those intervals approximately should capture the true parameter. Of course, we can adjust the confidence level. We can change it to 99% to increase our confidence. And I hope you saw that. The intervals going from 95% to 99% got a lot wider. And on this particular set of 50 samples, all of them now contain the population mean. So if I sample 50 more, all of those do too. We're 100 for 100 so far. Well, now I missed a couple, so I'm back down to 99%. So in the very long run, 99% of all these intervals, if I use a 99% confidence level, will capture the true mean. So there's a price we pay if we want greater confidence. We're going to have it look like a wider interval than what we had when it was 95% confidence. So we'll more likely capture the parameter value, but we're going to have a wider interval to do it. So our interval of plausible values for the parameter is much wider. So I love this little applet. It's quick. You can adjust the confidence level. You can take many samples, and you can ask students about what the confidence level means and what the relationship is between the confidence level and the width of the interval.
And there was a question about where this applet is available. This is on the book companion site?
This is on the book companion site. You can go straight to www.whfreeman.com/TPS4E, or you can use the BCS version that you see up here at the top of the screen. All of these applets are easily available once the site loads.
And that is for adopters of the practice of statistics.
Absolutely. All right, so we've shown our first applet, and it worked. I had a static screenshot just in case, but it's not nearly as much fun. So the idea, again, if we take many, many random samples of size n from that population and construct a confidence interval based on each of those samples, about 95% of those intervals will capture the population mean. So the big idea I want to leave here is confidence level equals capture rate in the long run. Confidence interval equals long run capture rate. So we saw one of the things that affects the margin of error in that last applet. We saw that the confidence level affects the margin of error or the width of the confidence interval. But we can study our formula and understand why that is, as well as the other thing that affects margin of error. The biggest one is sample size. Larger random samples give, I'm putting better, but more precise estimates than smaller random samples. We get better information if we ask more people than if we ask fewer people. And you can see, if you think about the formula, increasing the sample size is going to decrease the standard deviation of the statistic, which always has the square root of n in the denominator. And if that decreases the standard deviation, it's going to decrease the margin of error here. And we just saw with the confidence level, higher confidence is going to require a longer interval. And that is because increasing that confidence level increases the critical value that we see here. So that's going to increase the margin of error as well. So sample size and confidence level are the two big factors that we need to think about when we're thinking about our margin of error for our confidence interval. So let's get to that part about what students need to be doing for the AP exam. Once they get an understanding of what a confidence interval tells them and what the confidence level represents, we want them to set up their work on a free response question in the following way. We want them to identify their parameter. That is, what are they trying to estimate about this larger world out there? And what confidence level are they using? In most AP exam questions, they're going to be told the confidence level. So the key piece here is defining that parameter carefully so that it's clearly not about the sample data. A lot of students will start talking about the value of their parameter, and then you'll realize that what they're actually describing is their statistic they got from their sample. So that's not how we want them to start. We want them to talk about this parameter value. Then we want them to talk about what method they're going to use and check any conditions that are required before they use that method. Then we want them to do the work, and I'll explain more about that in just a second. And then finally, we want them to interpret that interval, the interval, not the confidence level, but the interval in the context of the problem. And that's what we did back on the first example. Now, the conditions for doing inference depend on whether we're doing inference about a proportion or a mean. So I'm going to hit the one first that's for both. We need the data to come from a random sample or a randomized experiment, a well-designed random sample or randomized experiment. That allows for the scope of inference that I talked about earlier, and it also introduces chance into the design so that we can put a probability model on top of the design to look at how things will vary. Then we need something about normality of the statistics sampling distribution, approximate normality at least. So for proportions, we need to check that n times p and n times 1 minus p are both at least 10. For means, we have two ways to get approximate normality of the sampling distribution. If the population distribution is known to be normal from the problem, we're good. Then we don't need to worry about sample size. But in most real-world problems, we don't know that, so we have to have large enough sample size. And for purposes of simplicity, we like to say if n is at least 30, we'll proceed assuming that we have large enough sample size. We also need to think about whether individual observations are independent. And the key here is if we're sampling without replacement from a finite population, we don't want to take too large a percentage of the population out because we're assuming that things stay constant throughout the sampling process. So students do need to be aware that there's this 10% condition that we ought to be aware of when we're sampling without replacement. So let's look at getting a confidence interval for a proportion. Here's an actual example from the annotated teacher's edition that goes with TPS 4E, a humorous one. So according to an article in the San Gabriel Valley Tribune, most people are kissing the right way. According to this study, the majority of couples tilt their heads to the right when they're kissing. Bet you didn't know that. In the study, a researcher observed a random sample of 124 couples kissing, what a great study, in various public places, and found that 83 out of the 124 tilted to the right. That was 66.9%. So we want to construct and interpret a 95% confidence interval for the proportion of all couples who tilt their heads to the right when kissing, based on that random sample. Well, if we had to make one guess, we would guess the proportion would be about 0.669. That would be our point estimate based on the sample. But we know that our random sample probably didn't get us to exactly the value of the population proportion. If we took a different random sample and observed the couples kissing, we'd probably get a different proportion. So let's go through this process. First, we want to state the parameter clearly. So P is the true proportion of all couples that will tilt their heads to the right when kissing. And we want to estimate it at the 95% confidence level. Now we want to check our conditions for using a one sample Z interval for the proportion, a assuming that the normal condition is met, we'll be able to use a standard normal distribution to get our critical value. The researcher was said to have observed a random sample of couples, so the random condition is met, and that will allow us to generalize our findings to the population of all couples. To check the normal condition, we don't know the true value of the population proportion, so we use the sample proportion instead. And you'll notice that n times p hat is really just the number of couples that kissed while tilting to the right, so that was 83. And this is the number of couples that didn't kiss tilting to the right, but tilted the other way, so that's 41. And the 10% condition here, we're sampling without replacement, so we hope that there are at least 1,240 couples out there in the population. Since our conditions are met, we're able to proceed to calculations. So for those of us who are math teacher types, this is how we envision the calculation looking. We have our point estimate, or our statistic, plus or minus our critical value, z star, times the standard deviation, well, actually the standard error of our statistic, square root of p hat 1 minus p hat all over n. And we've plugged in our sample proportion. Most of us who've taught statistics for a while have memorized this critical value for 95% confidence, 1.96, or almost 2. And then we've plugged in our sample proportion here, 0.669. So that yields an interval 0.669 plus or minus a margin of error of 0.083, or an interval of 0.586 to 0.752. For those of us who are more contemporary, we might actually go to our TI calculator and use some kind of function on the calculator, like 1 prop z int. And if we do 1 prop z int, we get this interval. And some of you might be wondering, well, can students do that? Or do they have to show the formula and plug in the numbers? Actually, on the AP exam pre-response, a student who does 1 prop z int and writes down that interval gets the credit for doing the do step. So that's all students have to do. Now, if they get it wrong and they write down the wrong numbers on their paper, then they're not going to get any credit for just writing that down from the calculator. But it does save time, and more students get it correct if they use the calculator feature. So there's a little bit of a risk-reward for using the calculator. They might be more likely to get it done correctly and quickly, but they also might make a typo or a transcription error, in which case they might lose all credit. So most of my students tend to gravitate towards the calculator as the course goes on, and as I allow them to use it more. But I'm kind of old school, as some of you know, so I like to show the formulas first and insist that they try to master those. But again, to get full credit on the AP exam, this little calculator information here is sufficient for the calculation or the do step. And now our conclusion is where we interpret our interval in context, and we say we are 95% confident that the interval from 0.586 to 0.752 captures the true proportion of couples that tilt their heads to the right when kissing. Q time. So that's what we're looking for on the AP exam. We want parameter defined, name of the test or interval with conditions checked, the result of the calculation, and the interpretation of the interval. I'm taking a little pause because I'm about to jump to confidence intervals for means. Cindy, how we doing? Okay over there?
We're doing fine. Everybody's got sound and paying attention. Yeah.
Outstanding. So let's talk about confidence intervals for a mean for just a minute. And this question of why can't we just use Z? That would be a lot easier. We've learned the standard normal distribution. The kids are really comfortable with it. Whether you use the old table A that has the normal probabilities, or whether you let them use technology with inverse norm. Let's talk about why we can't just use Z. So this is our formula for a confidence interval. If we know the population standard deviation sigma, which only happens in your dreams, then we could just do this. This is called a one sample Z interval for mu. And a few of us who've taught long enough remember books where you spent time going through calculations like this, and you may have even spent an entire section on it. But let's get real. You're not going to know sigma if you don't know the population mean. So maybe what we could do then is just use the sample standard deviation instead. Just plug in the sample standard deviation S sub x instead of the population standard deviation sigma. Sounds like a good idea. So let's try it. Let's try constructing a 99% confidence interval for a population mean based on a simple random sample of size 4 from a truly normal population that has a mean of 100 and a standard deviation of 40. So it's kind of the ideal case. Simple random sample, normal population. I've even told you what the mu and the sigma are. So then we'll know if we captured the mu or not. And again, I'm gonna pop out of my slideshow and try it with an applet that I think is really effective for showing this. So the applet I'm going to this time is at the Rossmann Chance website. You can see the URL up in the top toolbar. Just remember rossmannchance.com. They have some nice free applets. This particular one is very nice because it allows you to do what I want to try to do. Do inference about a mean using a z critical value from the standard normal distribution and using the sample standard deviation S from the data. So if I've set my mu at 100, my sigma at 40, my sample size at 4. If I click sample, it will, ooh, look at that, my first one missed. That's not a good sign. I'll click another one. There we go. Green is good, and red is bad. So we like to see green. We don't like to see red. So what I'd like to do is run a bunch of these confidence intervals at 99% confidence. And so I'll do maybe 100 of them. Now, what sort of capture rate would we expect if everything's working properly? If we do a 99% confidence level? I'm thinking 99%. Let's try it. Well, I took 100 intervals, and 90 of them out of 100 captured the true mean shown by the vertical line in the middle. That's not real good. We were claiming a 99% confidence level. Maybe I just got unlucky. Let me try another 100. Well, that time, 90 out of 100. We're sitting at 90% exactly. I'm having really bad luck tonight, Cindy. Bad luck. So I'll try another 100. 90 out of 100. Oh, there we go. I got 92 that time. If you do this for a while, you might think, oh, I'm going to get luckier. So I'll do about 2,000. And you can see my capture rate so far in the long run is about 92.6%. This isn't working. I'm not getting the capture rate I'm supposed to be. And part of it, if you take a look at, here's my next sample of 100, some of the intervals are really short. The standard deviation for that sample is quite small. If you focus on the dots that come up here, you can see how spread out they are. So this sample had really small standard deviation, and it just didn't stretch out far enough to capture that population mean. So sometimes we get an unlucky mean that's far away from the true mu, and sometimes we just get a really small standard deviation, and when we multiply by 1.96, our interval's not long enough. This is such a cool applet, though, just to show you it doesn't work. And if it doesn't work, you got to try something else. So what to do? Well, those of you who've taught it before know what you have to do. You can't use z. When you standardize a normal distribution from a sampling distribution of x bar, you get a standard normal curve. But we're going to divide by sx over the square root of n instead of sigma x over the square root of n when we standardize now. Up here we got the sigma, down here we got the sx, and this thing is called a t-statistic, and I have a little file to show you a little demo on that from Fathom software. So this is the same problem, mean of 100, standard deviation of 40, and I've got Fathom set up to be able to do several random samples. And for each of these random samples, I hope it will calculate the value of t and the value of z that I was mentioning before that should be standard normal. So far it looks like I've managed to freeze the Fathom software. That was pretty fast. It did about 6 and then it froze up. So I'm going to let it keep running for just a second. We'll see what kind of values we get here on the dot plot. I'm a little worried that some of the values I'm getting are a little strange, so I may try to reload this and do it later if that's all right. That's not looking too good. Yeah, let's not sit here and watch the thing spin. So the distribution that we get of this statistic, which we'll try to go back in and look at when it's done, should be a t distribution. And the number of degrees of freedom, it's called, is the sample size minus 1. So unfortunately, there's a different t-distribution for every sample size. That's not very much fun. There's only one standard normal distribution. All right, so that ends part 1, confidence intervals. My goal on this next part is to give you an introduction to hypothesis testing without getting quite as detailed. I wanted to really get into the details with the confidence intervals and do the big picture view of the hypothesis test, figuring that most of you are going to launch into confidence intervals first. So let's talk about testing a claim for a minute. So the idea of a significance test is to assess the strength of evidence against one claim in favor of a counterclaim. The evidence against one claim, that particular claim is the one we'll designate as the null hypothesis, and the counterclaim is the one we'll designate as the alternative hypothesis. Well, we got a different applet we're going to try. Hopefully it'll work as well as the first one did. This one's at the PPS4E website, so I have good faith, Cindy, that's going to work perfectly.
There was one suggestion to turn off the animation.
Yes, that definitely would have helped.
Yes.
I'd sort of hoped that maybe it would do it live, but no luck there. So I'm going back to the Practice of Statistics website. I'm going to go to the statistical applets, and I'm going to launch into the test of significance applet. This is one I used on the first day of teaching about significance tests. It's an old school free throw shooter. Notice the short shorts, and wait till you get to see his technique. When I use this applet as a teacher, I like to go ahead and cheat before my students get in the classroom, and I clicked on the Show True Percent button. And that shows me that this guy's really a 50% shooter. All of the shooters claim to be an 80% shooter, but some of them really are not. Some of them are exaggerating. So what I like to do is click on a new shooter until I get one who is not quite an 80% shooter, but close. So this looks like this guy shoots just under 70%. And now I'm going to turn off Show True Percent so the kids don't get to see that, and I'll show them the null hypothesis. That's 80%. So some of the shooters really are 80%, some really aren't, and the kids don't get to know which one I'm picking, but I'm telling you, I usually pick one who's slightly below 80%. So what you can do when you've got the applet set up is click Shoot. Watch this technique. He's got a little bit of an old school push shot going. For those of you who are sports fans, he also always goes what I'm going to call wide left when he misses. You'll see he always hooks them if he misses, so that's a technique problem. And we're monitoring over here the proportion of shots that he makes out of his first 25. At the end of 25 shots, I'm going to stop and ask the students, so what do you think? Is this guy really an 80% shooter? Well, we know the answer because I showed you the secret. He's really not, but they don't know. And what some of them will say is, no, I'm not sure. Shoot some more. Shoot some more, Mr. Starnes. Let's take up some more class time. So I will humor them because what I want them to think about is the condition for doing inference is n times p, and n times 1 minus p has to be at least 10. And with only 25 shots and a 0.8 success probability and a 0.2 failure probability, we haven't made it to at least 10 on both of those. So once we get up to 50 shots, 50 times 0.2, which is the failure probability, is 10. And we're good to use the inference techniques that are based on the normal approximation. And it's also fun here because now he's up to a 74% shooter, and things have just gotten interesting. Because I can say to the kids, well, now what do you think? We've got more data. We know more data from random sampling is good. And now a lot of kids will say, yeah, you know what? I think he could be an 80% shooter. But we're secretly laughing because we know he's not. And they would make the wrong decision if they went with that. So I love the applet because it gives you the freedom to choose whether the null hypothesis is true or false. You can make it a tough call or an easy call. And you can start asking questions like, what if this guy was a 50% shooter? Would we be able to tell that more easily than if he was, say, a 70% shooter? Which one would be easier to figure out? So we're actually getting at some of the big ideas of power of a test. Much easier to detect that he's a 50% shooter than he's a 70% shooter. Naturally, we picked like 70%. So this is the applet that I launch into things with. Again, the claim that he makes that he's an 80% shooter, P equals 0.8, and the alternative hypothesis for this applet is always that he's exaggerating. What else would an athlete do? I mean, he's going to go in his favor, right? So the alternative is P is less than 0.8, the one-sided alternative hypothesis, we call it. And now to think about the probability, or the p-value, I want to put this out on the slide. Assuming the null hypothesis is true, which is what we do when we do a significance test, the probability of getting a sample result at least as far from the null parameter value in the direction specified by HA as the observed result. That is a really difficult concept for students because it just has so many little clauses in it. So assuming the null hypothesis is true, the probability of getting a sample result at least as surprising as the one we just did, like 0.74 was what we got for the shooter, in the direction specified by the alternative, which was less than 0.8. To me, 0.74 doesn't sound that surprising when the null was 0.8. More surprising would be a lower number. But the question is, how likely is it to get 0.74 or less when the null hypothesis is true? So I do write this in symbols. The probability of getting a sample proportion less than, and we could put 0.74 right in there, or equal to 0.74, I should have an equal to sign there, given that P equals 0.8. It's a conditional probability. All right, I heard this at a workshop. P-value low, the null must go, right? Low P-value means it's really unlikely to get a result like the one we observed if the null is true. So in that case, the null doesn't seem believable anymore. P-value low, the null must go. I heard a few other things at that workshop, but I'm not sharing them on this webinar. People have some clever ways of remembering these things. So here's the big idea again. An observed result that is unlikely to occur just by chance when HO is true gives evidence that HO is not true. So if that guy had made like 65% of his free throws, I think 64% is what he made in the first 25. If he had kept that up, I think I would really doubt that null hypothesis. We would have really strong evidence against the null. So that's the logic behind it. The mechanics of the test are more involved, but I think the big ideas need to be out there first. So if we were going to do a test, we would state our hypotheses. There they are again. And we've identified our parameter value again. So just like with confidence intervals, we start out by stating what kind of inference we're going to do. And then we tell what kind of procedure we're going to use if the conditions are met. So this would be a one proportion Z test based on the standard normal distribution. We have a random sample of shots from the computer-generated applet. Our normal condition, I mentioned out loud, is met just barely. N times 1 minus P is exactly 10. And in this case, we're not sampling without replacement because it's an infinite computer-generated applet. But I might mention something about one shot's outcome really tells us nothing about another's because it's being randomly generated. The do step, I'm going to set it up in the format that you might expect. We calculate a test statistic, assuming that the null hypothesis is true. So you can see I went ahead and plugged in everything except for the value of the sample proportion because I didn't know what we were going to get. So we would plug in 0.74 there as our p-hat value, and we would compute our test statistic. And then because the normal condition is met, we can go to the standard normal distribution, either on a table or on our calculator, and we can calculate this p-value, this conditional probability. In our case, we would plug in the 0.74 there, calculate our z statistic, which would be a negative number, and we would look up the probability of getting z less than that negative number on our table. And then we would draw our conclusion based on the p-value that we got. I've actually put the template here because this is what I'm trying to give my students as a helpful way to fill in the blanks. So the first part of the conclusion is, because the p-value, whatever we just got up here, is greater than or less than alpha equals 0.05, we either reject or fail to reject the null hypothesis. Those are our two permitted conclusions. And then the final sentence is, we either do or do not have convincing evidence in favor of the alternative hypothesis, which is that the true proportion of free throws this shooter makes is less than 0.8. So this is the template for a hypothesis test. Notice also that the do do step, once again, could be accomplished with the TI 84 or 83 or 89, the calculator one prop z-test function. And if kids do that instead of showing all the work, they're taking a bit of a risk in case they make a typo or write it down wrong. On the other hand, if they say one prop z-test and they write down the correct answer, they get the 1 point for the do step. Some of you know that there are 4 points assigned on inference, or on the pre-response questions on the exam, and these 4 parts match up really nicely to those 4 points. So 1 point, 1 part. It's easy to kind of give the kids a sense of what they're going to score based on how they do on each of the parts. So let's talk about what can go wrong or right when you do a significance test, and then I'd like to get to the idea of how that interconnects with the power of your test that I mentioned earlier. And then I'd love to have some time to open it up for your questions. So here's a little graphic that you see in the textbook. There are 2 possibilities in terms of the truth about our population. The null hypothesis is true. In our case, that would mean the guy really is an 80% shooter. And the other is that the alternative hypothesis is true. He's really exaggerating. He's less than an 80% shooter. Then on the other side, there's the conclusion we get based on the data. And our 2 decisions that are permitted in statistics are we reject the null or we fail to reject the null. Do not let your students do anything that sounds like accepting the null. That will be a deduction. Anything that sounds like that. Just have them use these 2 phrasings, reject the null or fail to reject the null, and that's it. No freelancing on the words. Now, there are 4 scenarios. If the null hypothesis is true, and we decide to reject the null hypothesis, then we've made a type 1 error. That's not good. If the null hypothesis is true, and we, based on the data, don't reject the null, then we've made a correct decision. But if HA is true, and this guy's exaggerating, then we really should reject the null. And you can see the happy face there. If the alternative hypothesis is true and he's exaggerating, but the sample data lead us to fail to reject the null, that means we don't detect that he's really exaggerating, and we make a type 2 error. So this distinction between type 1 and type 2 error, those are the 2 types of errors we can make before we actually go out and collect the data. Once you've run the test, there's only one of the 2 types you could make because you will have already made a decision based on the data. So there's only one type left to make. So before you collect the data, you have 2 types of error you could make: rejecting the null when the null is true, type 2 error, failing to reject the null when the alternative is actually true. And I heard it again at a workshop, fail to, type 2, helping kids remember which is which. Fail to, type 2. Kids do get them mixed up. Some of you know this, and so a little helpful mnemonic is worth a lot so they don't get them backwards. I've got one more applet that I want to try out for power. Type 1 and type 2 error, the interconnection. This applet is courtesy of the American Statistical Association. And I'm going to open up the proportion applet. Well, that's not working too well, is it? I'm going to reload. We're having a little trouble with that applet, Cindy. Doesn't look like it's loading. Well, shucks, I may have to go to my static image. Let's do that. And again, I'll try to get the applet to show up later. So here's an image of the applet. Usually works quite nicely, but we're having some simulation difficulties over here. May have frozen up my Fathom and messed up my simulation. This is a picture of the applet, and what I've done here is I've put the null distribution for the free throw shooter at 80%. You can see I've set over here the value of the null hypothesis of 0.8. I've had him take 50 shots virtually on the applet. I've set the significance level at 0.05. And I've placed this alternative distribution a little bit to the left. It's actually centered 0.15 units to the left of 0.8, so it's at 0.65. So the question here is, if he's really a 65% shooter, how likely am I to figure that out based on a random sample of 50 shots and an alpha or significance level of 0.05? The significance level is shown here in green. That's the alpha level. It's the probability of making a type 1 error, chance of rejecting the null when the null is actually true. On this side, we can see the alternative distribution. If he's really shooting 65%, that means anytime we get a value of a sample proportion to the left of where my arrow is, we're going to reject the null. And that's most of the time. Actually, it's 80% of the time, we can see up here. So the probability of detecting that he's really a 65% shooter under these circumstances is about 80%. So if we want to try to increase our power, there are a couple of things that we can do. One is we could increase the sample size, because that will decrease the width of these two overlapping curves, and that will make it much easier to detect such a large difference as 0.15 in the proportion. The other thing we might do is adjust the alpha level. If we increase the alpha level, then that will increase this blue area at the same time, because this cutoff will slide to the right. This is my best attempt at a static dynamic applet. So those are really the two things under our control: increase the sample size or increase the probability of a type 1 error. So that has its own risks if we're going to be doing a significance test. We really want a higher type 1 error probability. So the advice I usually give my students is choose the highest type 1 error probability that you feel comfortable with, and then the largest sample size that you can afford. That's usually a budget issue. You can't just go out and do your testing on hundreds and hundreds and thousands of people in all cases. All right, let's see how we did, and then I'd like to try to clean up some of the loose ends there. So my goals were distinguishing the proper interpretations of confidence interval and confidence level. We did that early on. Trying to help clarify the underlying logic, but not all the details of the significance test. Tried to give you a template to show you what it would look like, but we didn't fill in all the details. Showing the link between the type 1 error, the type 2 error, and the power that was on the that last applet slide. Showing you the 4 things that students really need to do for that 4 points on the inference questions for those FRQs. And then talking a little bit about strategy, how we would teach students along the way to do inference correctly. So focusing on interpreting the confidence interval and confidence level being a separate issue. Trying to use the 4-step process to organize their work. Using technology as a tool to help them avoid calculation errors, even though it comes with a little bit of a risk. Okay, I do have one final thought before we take questions. H-O-H-O-H-O. It's that season. So I think it's time for some questions. Cindy?
Can we have the citation for the Amstat article on the last applet page?
Absolutely. I can't make the applet run, but I can show you the URL here. So this is a long URL. I found it by searching on power applet for proportions. And this is at the Journal of Statistics Education, the American Statistical Association site. It's another free applet. And sometimes when you do free applets, you get what you pay for. Tonight I got not a whole lot going on. But I swear I saw it earlier. It is a really nice applet. It shows everything you need to see when you're dealing with proportions. Fire some more questions at me, please.
Anything else? Lots of thank yous.
Wow.
This was great. Wish I could stay longer. Have to go to a meeting.
Some of them probably have to go holiday shopping.
Any other questions you want to ask Daren about inference? Null hypotheses?
So I'd like to ask one question for those of you who are still there. How many of you are new at teaching AP statistics? How many new folks? Show of hands. We had a couple of new folks out there earlier. All right, so, all right, how many of you are grizzled veterans? That would be 3 years or more. Doesn't take a lot to be a grizzled veteran in our course.
Yep, here come the hands.
Okay, 3 years or more.
5th year, veteran.
A couple of you are very grizzled.
Very.
Yeah, okay, all right. teaching for at least 3 years, what I want to see now is raise your hand if you've applied to be an AP reader. Some of you are AP readers because I can see who you are. If you haven't applied yet, you've been teaching for 3 years, we'd really love you to consider that. We have a lot of people on this presentation actually who are experienced readers, and probably you guys should be doing this thing, but I'm flattered that you're here. I hope you've gotten something out of it that you hadn't seen before.
And a few of you have asked about the presentation. We did record tonight's session, and we'll be sharing the link and the PowerPoint that Daren presented, so you can get the URLs, which are hyperlinked, and hopefully will work on your own machine when you have lots of programs already running. So yes, thank you for your interest, and you will receive a follow-up email from me with a link to the recording and attachment of the PowerPoint.
And I'm really serious. I hope some of you will consider using the example that I opened up with. It's one that we're trying out on a test audience. That would be you. And I'm going to be trying it out on my student test audience. It's a new example that we're sort of playing around with, and we'd love your feedback if you try it with your students when you get to confidence intervals. Is there a good way to remember the difference between by type 1 and type 2 errors, a mnemonic for the? Yes, the one that I heard in the workshop that I sort of liked, that I shared with my students is, remember a type 2 error is when you fail to reject the null hypothesis when the null is actually false or the alternative is true. So fail to goes with type 2, fail to, type 2. So they both got 2 in them, I think, is the punchline. Seemed to work well for my students last year, actually.
Type 1, The Fugitive or Shawshank Redemption?
Uh-oh. We got more good ideas coming in there. And I also wanted to invite folks, if there's anything that I said in the webinar tonight or something that you want to try out in your classroom, please feel free to email me. I'm happy to correspond with you about things that you try, and curious about your experiences in the classroom.
Very good. Any other questions, feedback for Daren?
Well, I want to say happy holidays to everybody. I hope you all get a chance to get a nice break.
A request to go back to the textbook resource page.
Okay, we can do that. Here's the Practice of Statistics website. You notice you can follow the cookies backwards here to the statistical applets or to the actual homepage for the book website, which shows you everything that's there. I've got the applets expanded right now, but you can track those, or actually you can click on them and go there again. Seem to be mouse challenge tonight. There's some really nice things there if you haven't explored lately.
Are the Fathom files aren't embedded here? Those are.
The Fathom file is not embedded, but I can certainly, if you email me, I can attach the Fathom file back to you for you to play around with. I think I need to fix something first because it didn't seem like the values were coming out where I expected them. You notice I didn't go back to it.
There are Fathom files referenced in the notes of TPS, and she's wondering where they are, where those Fathom files are.
Yes, if you email me, I'll get you there quickly. Otherwise, I'd have to read out URLs and things, but yeah, I'll be glad to get you there if you email me.
Okay. Just make sure I didn't miss any.
Cindy's just scanning the question list.
Yeah, so the site that Daren's showing now, this is for adopters of the Practice of Statistics 4th edition. If you've purchased at least 6 copies of the book or more, you are eligible to receive this complimentary from your sales representative. And if you don't know who your sales representative is, you are welcome to email me. You all have my email address from the invitation to tonight's session. I'm happy to put you in touch with him or her.